Welcome. So just this morning, a while ago, I sent around just this updated information for the class tests. So the alphabet split is there, so we're going to take everybody with surname A to K at the 11 o'clock lecture down in Jeffrey Mountain next Wednesday. And if your surname L to Z, we take you at 12 o'clock. Okay? Please attend the correct slot for your timeline for your surname, so we can have some numbers. If you have a PLP which has changes for your assessment arrangements, I've already emailed you, so check your email and there's time and location for your test. Now, just a little bit of updated information. Discussions with Saeed, we decided to take the complex numbers off the test. So there won't be any questions on the complex numbers. We dealt with that a bit in the first test, and it may still feature, of course, in the second exam. So in terms of the topics, it's just the integration material from Saeed and the, well, mainly the differential calculus material from myself. That may refer to some other elements of the functions as well. The two mock tests there, I've typed up all the solutions to mock test 1. I'll do so for mock test 2 and get them up there as well. And I've also picked out the video from last week, or the week before. Last week, I think it was, where so this video just from this week. Last week, we solved the two optimization problems and feature on the mock tests. So just highlighted that video there for you as a reminder. Okay. So what I'd like to do today is just show you some things, some important topics from my part. And I did get I got an email from Chris, I think it was, who was requesting just a little bit of discussion of the question 3 from the mock papers. So we'll just go through the solution to question 3 again. And I've got a few more things I'd like to show you as well. Okay, but as we go through these, please do stop me at any time if you want to ask questions. If there's anything you want clarified from this, okay? Okay, so we're looking at the first mock paper, and this is question 3. So this is question 3 here. So it's an exercise about the limit definition of the derivative. So it's asking you to quote it. It's asking you to quote the definition and to demonstrate your ability to use it. Demonstrate your ability to use it to work out the derivative of a given function. So for this kind of thing, to get the full marks, we want to clearly give the definition very clearly. So the derivative at x equals a of a function f, we can assume that f is going from the real numbers to the real numbers. The derivative at x equals a of a function f is written, we'll write it as f dash a, and it's given by, well, I mean, you're prompted there in the question to give the limit definition of it. So you need to accurately quote this limit, and it's the limit of the relative change in value of the function. Okay, the quotient there, f of x minus f of a, is the change in value of the function between x and a. Scaling it by x minus a makes it the relative change. The amount of change as a proportion of the change in the argument. And then we're taking the limit of that as x approaches. Alternatively, the other way of saying it, where instead of a separate point x, you think of a separate point a plus h. And then the denominator simply becomes h, and we're taking the limit as h approaches 0. That would be perfectly acceptable. That would be perfectly acceptable as well. Okay. Okay, so let's see if we can apply this in the case of the reciprocal function given here. Okay. For the function g of x, which is 1 over x, and we could choose either of these to use. I'll use the x and a one, but just minor adjustments, it would work with the h version as well. So the derivative of g at a point a, well, we should first of all just say that we would have to assume that a is non-zero. Function g of x is not defined at 0 at the moment. So first of all, we just might repeat the definition again in the appropriate notation. Now we're talking about the function g. You don't absolutely have to put that line, but it just helps to set it up and reassure yourself with it. And now you can put in the definition of g, because of course 1 over x, so g of x is 1 over x, g of a is 1 over x. Nothing too astounding there. But we do need some careful manipulation of this, because you can't simply evaluate that limit directly. You might want to use the algebra of limits theorem, the quotient form, and say the limit of this quotient is the quotient of the limits. But unfortunately, both parts are approaching 0. So you can't say it's 0 over 0, because 0 over 0 doesn't mean anything. And we don't want to go talking about L'Hopital's rule, because L'Hopital's rule relies on the existence of the derivative. But here we're in the middle of an argument trying to prove the existence of the derivative for this function. So we don't want to go appealing to the derivative of it when we're trying to establish it. So we need a kind of algebraic way to proceed. And the way to do it is to, well, bring these two functions together. So we're leaving the limiting process alone at the moment. The limiting process is still sitting there. But we're just working in the fraction, and we bring these two fractions in the numerator together. So it becomes, we can have a common denominator of x times a, and then the numerator will be a times x. Give us 1 over x minus 1 over a. But now we can see a way to proceed, because that can be simply written as we've got x times a in the denominator, x minus a in the denominator. And what we're seeing in the numerator is, just to emphasize that it's really the same factors in the denominator, we can write it as minus x minus a. And so it's clear what can be done is these factors can be cancelled. Divide above and below by the quantity x minus a. You don't run into any problems with division by 0, because you're taking a limiting process as x approaches a. So x is never at a at any point in this limiting process. It's just getting closer and closer to a. So there's no barrier preventing us from rewriting the fraction by dividing above and below by this point. Okay, so that's simply cancelling x minus a. I mean, that's just straightforward algebraic manipulation. We don't necessarily have to make any justifications there, except it might be helpful just to say we're preparing the fraction before taking limits. that's what we're doing. We can take the limit immediately using any standard property of the limit. So we're examining the thing we're trying to take the limit of. But now at this stage, we can take the limit immediately. We can just simply substitute x equals a, okay, using the algebra of limits. So that will become minus 1 over a squared by the algebra of limits here. No complication about something over 0 or limits not existing. X is getting closer to a, so x times a is getting closer to a times minus 1 over a squared, as required. So we can say the derivative function of 1 over x is minus 1 over x. Because at any point a, or at any non-zero point a, any non-zero point, the derivative is that expression, minus 1 over the square of the argument. Okay? So is that okay? Any queries on that? So, let's try doing a similar one from the Mach 2. So the Mach 2, we won't spend as long on it because it's quite kind of similar, but it talks about the function 1 over x squared. Hopefully we can do that. So we'll look at the Mach 2 paper. There it is. So it's a very similar kind of question. See there at the bottom. Except this time we're talking about the function 1 over x squared. Let's just check that it can be solved using the same approach. So here we would be doing that the p prime of a. Well, let's now try it the other way. The limit of as h approaches 0, g of a plus h minus g of a over h. Show a bit of variety. Show that either approach can be made to work. So the limit as h approaches 0. Well, g of a plus h is 1 over a plus h all of it squared. And g of a is minus 1 over a squared. And h is h. So we can't do anything with the limit immediately, directly, using the algebra of limit 0, because as a goes to 0, both the top and bottom are approaching 0. So we got to do some preparatory stuff, and maybe the algebra might work out slightly differently in this case. We're talking about the square function, and we've opted for this h version. But you still keep calm and adopt the same approach. So you're looking at this common denominator, the square of a plus h times a squared, and the numerator, when you put this previous numerator over into this smaller numerator now, it's going to be a squared minus a plus h all squared. Yeah. So then that up here, we just got the difference between these two fractions. Okay, it looks a little bit more complicated with squaring, and maybe the h isn't so straightforward here. But let's try and do this. So we've got a plus h all squared, a squared, and a h down here. And what have we got in the numerator? Well, see, there's going to be some cancellation there. We've got the quantity a squared, and then we got the square of this. So we better expand out this square here. So that will be a squared plus 2ah plus h. So it makes sense to expand out that bracket because part of it is going to cancel there. Which is good. Don't think there's any need to expand out that bottom bracket. So we've got the limit as h approaches 0 of this bottom. Well, the a squared cancels, and we've got minus 2ah minus h squared. Well, we've got a plus h all squared, a squared h. So there's further simplification to do there. Of course, there's now, well, there's a factor of h in the denominator, and there's at least a factor of h in the numerator. So we can cancel h. So again, this is preparing for limiting it. We're almost there, but now we just cancel the h. So we have 2a minus h all over, what have we got? A plus h squared, a squared. No real way to simplify that anymore, I don't think. But now we check and we take the limit, we carry out the limiting process now. Well, there's nothing stopping us taking the limiting process now. Of course, in all of this, we can assume that a is non-zero. The function isn't defined at 0, so we can assume we're not dealing with a being 0. So, well, in that case, when you take the limit as h approaches 0, the numerator is approaching a non-zero limit, 2a, as is the denominator, a to the power 4. Yes.
Isn't it minus 2?
Excuse me, sorry, yeah, I dropped my minus sign there. Yeah, thank you for that. And yeah, so there's nothing stopping us applying the algebra of limits here. Quotient point. The limit of this quotient is just the quotient of the limits. Even just to, you don't necessarily have to write it out in all this detail, but just to emphasize what's going on. The limit of the top plus the limit of, over the limit of the bottom. Limit as h goes to 0. So that's minus 2a is the limit of the top, and the limit of the bottom is going to be a to the power 4. Which is, of course, minus 2 over cubed, as we expected. As expected from the question. The question told us that was what it was going to be. So, indeed, the derivative function g prime of x is minus 2 over x. But no, maybe it's a little bit more to it since it's to do with the squared reciprocal function rather than just 1 over x. And I don't know, maybe the h approach is a little bit, maybe there's one or two extra steps in there. But it's good just to be able to do it both, just to be competent in handling it. Okay, any questions about that? So that's using the algebra limits. We'd like to indicate where that's being used. We went to a fair amount of trouble to prove it in full detail, just from the definition of convergence. Well, we did it in the definition of convergence of sequences. I think that we allowed ourselves to operate it at definition of convergence for functions as well. Okay. So what I plan to do is I've got the optimization question I showed you last time about the pipeline going across the river. I'm going to talk about that because I think that's it's a nice, moderately complicated one. But before that, I'd like to also look at question 4 on Mach 2. Just because the question is worded in a certain way and it's asking you to show specific things at the question 4. So I just thought it'd be useful to make some comments about it. It's question 4. And it does match how we proved the quotient rule in the lectures. So this question 4 presents you with the quotient rule. It presents you with the quotient rule, the rule for finding the derivative of a quotient of functions, or the rule that shows you how the derivative of the quotient relates to the derivatives of the individual terms. Okay. But now the question is, what the question isn't doing, it's not asking you to prove it from all the way from first principles, all the way starting from the definition of the derivative. And what it's asking for is show how the quotient rule can be deduced by an application of the product rule, chain rule, and the derivative of the reciprocal function. The derivative of the reciprocal function is what we did first today. The derivative of 1 over x is minus 1 over x squared. So 1 over x is the reciprocal. So we proved already now today that it's minus 1 over x squared. So it's asking us to use that, the derivative of the reciprocal function, 1 over x, the chain rule, and the product rule. So it's a neat question because it kind of assesses your knowledge and your ability to use all the rules together. Product rule, chain rule, and you just saw the reciprocal function. We proved all of those from first principles, right from the limit definition of the derivative. But we're kind of recognizing here that the quotient rule kind of isn't some completely independent property that requires its own proof from first principles. It is actually a consequence of these. And we always like to do this in mathematics. You know, if we've done some work, if we've gone to the trouble of making arguments from first principles for some properties, it's always good if we can use those properties again. You know, make use of them, consolidate it, build on it, rather than continually going back to first principles. So this Mach 2 question 4. And just to indicate to you the kind of things that you might want to get across in your answer to demonstrate your understanding. So maybe you should indicate we will be using the following properties. So if, no, I don't want to use F and G, so F and G are going to be used there. So what do I call it? Yeah, so phi of x is 1 over x, then the derivative of phi is minus 1 over x squared, that's the reciprocal function. And the product rule, so for functions phi and psi, you can say that the derivative of product evaluated at a point A is phi of A times the derivative of psi at A plus the derivative of phi at A times psi at A. These are phi, psi. Greek letters we often use for functions. So that's the product rule. And where else do you want to use the chain rule? The chain rule was if we had a composition phi after psi, taking the derivative of that and evaluating it at point A. Chain rule, this would be the derivative of phi evaluated at psi of A, derivative of the outer function, if you like, then that would be multiplied by the derivative of the inner function psi evaluated at it. So it's good to get down just explicitly in front of your eyes the things we need to use. So to begin, we re-express the quotient. We re-express the quotient function f over g as a combination of products, compositions, and reciprocals. Just one of each, really. So the point is, f over g, well, for a start, it's the product of f times 1 over g. So that's showing, how the quotient can be thought of as a product. And the 1 over g can be thought of as the composition phi after g, where phi of x is the reciprocal function 1 over x. So now, what was the quotient, f divided by g, now makes no explicit reference to dividing by. The reference to dividing by is kind of covered by this function phi. So now structurally, we just see f as a product, so it's f times this function in the brackets, and the function in the brackets is a composition. First applying g to the argument, and then applying phi to the reciprocal operation. So, is everybody okay with that? Those steps. Doing what the question told us. Getting down on paper the derivative of the reciprocal, the product rule, and the chain rule. And we want to use those to prove the quotient rule. So we're going to have to express our quotient, f over g, as an appropriate combination of those operations. So quotient of functions is not some wholly unrelated, independent operation. It is just a combination of these. So our derivative of f over g, evaluated at a, we can take it to be the derivative of this, evaluated at a. We just said f over g is that. Well, this, first of all, this is a product between f and the bracket by after g. So we should apply the product rule. So we look to our product rule. This is going to be f of a times the derivative of the bracket, whatever that is, evaluated as a, plus the derivative of f at a times the value of the bracket evaluated as a. So that's using the product rule. I'll probably label these as the product rule. The chain rule. So there's our application of the product rule. Shift over to the left in case it gets longer. Well, okay, f of a is f of a. Can't develop that any further. The derivative of phi after g, well, that's a clear need for the chain rule. It's a derivative of a composition. So we just read off the chain rule. It's going to be the derivative of phi evaluated at g of a times the derivative of g of a. So that's applying the chain rule to this quantity here. Derivative of this composition. So I'm writing down the chain rule just with psi replacing g. Then here we still got f prime a. There's no development we can do with that. And here, well, this term isn't a derivative. It's just simply phi after g of a. Well, we know the kind of result we're heading for has got g of a is in the denominator position, so we should bring that in now. So we can apply the definition of this phi function. So this is simply 1 over g of a. going on? What's going on? Chain rule. Chain rule and the definition of psi. Phi. There's one more place we need to bring in the definition of phi, because we got the derivative of phi. The derivative of phi is minus 1 over x squared. We got the derivative of phi evaluated at g. So this now converts this line into minus f of a g prime of a over g of a whole squared. Okay. So we're bringing in the definition of the derivative of phi. This is still what it is, plus f prime of a over g. So that's just the definition of the derivative. So each step, we're justifying each significant step with reference to properties we were trying to use. And at the moment now, this is the sum of two different fractions, but the quotient rule is just expressed as a single fraction. So that tells you what to do. Just force that to be a single fraction. Well, it's a sum of two different fractions, so you need to put it over a common denominator. Look at the denominators. What's the common denominator? Well, you can just take this quantity g of a whole squared. And what have you got? You've got you've just got this numerator, which is minus f of a g prime of a. Then you got this numerator f prime of a, but it needs to be multiplied by g of a to put it over this denominator. So we have the and that should be our quotient. Which, say for just changing the order in which they're written on the numerator, it is. It's just simply the two terms of the other way around in the quotient rule of the question. So, and this is the required. This is the required quotient. Okay. So what you notice in that argument is nowhere did we mention limits. We'd already done sufficient work with the ground level limiting operation definition. Sufficient work in that in order to establish the product rule, chain rule, and the results back to the derivative. So we don't need to go back again down to that level. We can just use these, those higher level results that we'd already established, which is what the question was asking. So always take careful note of the instructions in the question. Okay? Sometimes the question will be designed to assess your understanding of the limit definition. Other times it will be assessed to understand. To answer this question effectively, it kind of takes in all the properties and how they can combine. So always do take careful account of instructions given in the question. Don't just leap. I mean, I've seen students do this before. They kind of see something, they recognize an equation, and they just dive in and say, "Oh, I'm going to prove that the way one of the ways I know how to prove it," but without taking account of the specific direction. Always read through the questions carefully. So how's that? Any queries about any of that? So I wasn't just showing off on my using Greek letters here because I wanted to avoid. See, I knew I was going to be having an argument involving f and g. So when I was stating these rules at the top, I wanted to avoid using f and g because f and g already are playing a particular role in the way the question is asked. So I wanted to state these properties I was going to use using other symbols. That's a good point about mathematical writing as well. Don't confuse yourself, don't confuse the reader by using letters for multiple meanings. In any particular argument, the letters should have unambiguous meaning. I probably should have used a different letter than phi for the reciprocal function. We call that r of x or And then my phi and psi can be just representing any functions here. Okay, then. So I'd like to show you another optimization problem now. Now the optimization problem is one from the end of chapter exercises. And I introduced this last week. So is this question 27 at the end of page 72. So this question concerns a river. It's half a mile wide, running in a straight line, we'll assume. And we've got to lay a pipeline from one side of the river to the other and run it to 3 miles downstream on the opposite bank. Okay, but laying pipe on dry land is easier than laying it across a wide river for various reasons. We're going to, just for the purposes of the problem, so there's a multiplier on the expense. So laying pipeline underwater is going to be 25% more expensive than laying it on land. How should the pipeline be built in order to, well, we're talking about cost, obviously we want to minimize the cost. That's the question. So, you know, half the battle in this question is just laying out the information and setting things up correctly. Yeah. And often the diagram helps. Okay. So we've got our straight river. We've got 2 points A and B. And these are 3 miles apart, downstream from each other. We're told the river is half a mile wide. So the river is half a mile wide. So how should we build the pipeline? Well, you know, the shortest pipeline, of course, just goes like that. But that shortest pipeline spends all its time underwater. So that whole pipeline is going to be 25% more expensive than just building the equivalent straight pipeline on land. So that mightn't be the cheapest pipeline to build. Equally, if we go all the way down the 3 miles on dry land and minimize the underwater section, I mean, the underwater section has to be at least half a mile, of course. If we minimize the underwater section, so that will reduce the underwater cost, but we also kind of maximize the dry land cost. So maybe that might be the cheapest. So the thinking is there's going to be some intermediate kind of route that's going to go across underneath the water on some kind of diagonal, maybe slightly longer than absolutely necessary for going underwater. But what you're doing there is you're slightly minimizing the dry land length. Of course, every solution like that has a kind of a mirror solution which just goes down this side first and then across here. So it's kind of a parallelogram. Both sides of that, both going up here and across, or going across and up there, they would both cost the same amount because the same lengths underwater and above. Okay, that's all. Okay, so we can maybe make some observations like that. And of course, everything's going to be straight lines. And anything you can do with a curve, you can do at a shorter distance with a straight line. So these are obviously going to be straight lines. But we need to introduce a variable somehow. Introduce a variable or more to model this. Now there's no one way that's the correct way to do it. Various ways you might do it. But one thing we might do is we might we might have our axis here, starting at 0. So we'll have the 0 position on our one-dimensional axis to be at the location A, and so then 3 miles downstream is the location B. So at least we set an axis or a scale against our diagram. And so then the one point that's indicating how we're building our pipeline is the location of this point on the opposite bank that we go diagonally across. So we can give that a name. And if it's not being used, maybe we prefer x is equal to. So x is that quantity there. So the cheapest pipeline, the cheapest route, is surely determined by the value x. And what we know about x straight away is it's somewhere between 0 and 3. And we certainly shouldn't build a pipeline of this direction away from the destination first. Yeah? Or we certainly shouldn't build diagonally across the river to a point beyond B and then have to go back to B. That's obviously very wasteful. So our cheapest route is determined by some value of x. Okay. Then you might have measured with 0 starting from B or some other way, but some kind of way to indicate or zero in on the quantity that determines the route. So next we need the cost function. Which is C of x, which is going to be the cost of this pipeline. So x determines the route. C of x is going to be the cost of this route. So we assume a cost of 1 per mile on dry land and 1.25 per mile underwater. Okay, so it's 25% more expensive. $25% more expensive to go into the water. Clearly, this does not depend on how much it actually costs. $100 per $100,000 per mile on dry land or whatever the cost per dry land. It's really just the ratio between the two costs that's important. So we'll just assume a kind of unit cost per mile on dry land and a 1.25 per mile. So I like to think of 1.25 as 5 quarters. So what's our cost function? Well, the easiest part of the cost function is the dry land part. Dry land cost plus the underwater cost. And the dry land cost is probably easiest to write down. It's simply 3 minus x, isn't it? We've got to build that length of pipeline in dry land. The underwater cost is going to be 5 quarters times the length we're going underwater. Right. The length we're going underwater is the hypotenuse of this triangle. We've got this triangle, which is these side lengths, half and x. So we can just apply Pythagoras' theorem to get the length of the hypotenuse. Pythagoras' theorem says it's the square root of a quarter plus x squared. Okay, the hypotenuse is the square root of the sum of the squares of the other two sides. Everybody okay with that being the cost function? Makes sense? The dry land cost plus the underwater cost. There's clearly no maximum to the cost. I mean, if you want to be wasteful, you can build off in the wrong direction and then come back again. So you can obviously achieve any large cost that you want to do. But the interesting point is finding the minimum cost. Okay? So this will be minimized. Some solution of dc dx equal to 0. Yeah. You want this to be find minimum values of these continuous functions, differential functions, by setting the first derivative equal to 0. Those are the locations of the turning points, which may be maximums or minimums. Okay. Well, we kind of know ahead of time there is no maximum cost because, say, you just go off in the wrong direction and back again. You build any length of pipeline. So what is dc dx? So that's equivalent to -1 plus 5/4 times the derivative of this. And the derivative of this is going to be 1/4 plus x squared to the minus a half. It's going to be an extra factor of half comes from differentiating the square root. And we got to operate the chain rule and multiply by 2x as well. So we're differentiating the square root function, which is a half times the argument to the negative half. Then we're also operating the chain rule, so multiplying by the derivative of the inner function. So it's a non-trivial function inside the square root. So its derivative is 2x. So this has to be 0. So this is equivalent to -1, so we tidy this up a bit. And the 2's cancel. So it seems to be 5x over 4 times the square root of 1/4 plus x squared. And that has to be 0. Now, well, we can yeah, that's equivalent to saying 5x is equal to 4 times the square root of 1/4 plus x squared. Okay, to do that, we take the -1 over the other side and clear the denominator. And that would be equivalent to saying, so you can get rid of the complication of the square root by squaring both sides. 25x squared should be 16 times 1/4 plus x squared. So that'd be squared on both sides. Assuming x is bigger than 0. So you can see it come together now. We got 25x squared equal to 4 plus 16x squared. So that's equivalent to, you got 9x squared equals 4. So that's equivalent to x squared is 4/9. Which is 4/9, and that's equivalent to x is the square root of that. So the square root of that is 2/3. Which is great, the value for x. Probably even sketched it correctly, because that probably is about 2/3. That's 1, 2. 2/3 does look about right to sketch. So this is, okay, well, speaking, maybe we are not 100% sure this is a minimum cost. So we could check the sign of the second derivative of c and observe it's greater than 0, so x equals 2/3 is a minimum cost. Is a minimum cost root. But I think you can argue, but we can also argue there is no maximum cost. As we could let x be any value, any positive value. Build a stupid pipeline all the way down underwater, miles and miles away, and then come back again. So there's no maximum possible cost. So this stationary point we have, it must in fact morally be. So x equals 2/3 is surely a minimum. And it fits with our intuition that we kind of described at the start about how going all the way along dry land and then across water is kind of the longest reasonable pipeline. We tend to increase the cost. And going the shortest possible pipeline all the way underwater is probably too expensive as well, because you're underwater all the time. You're not taking advantage of the low cost of dry land pipeline. So there's some intermediate option is the option. Okay, I went a few minutes over there, sorry for that. But, we'll leave it there. So please take advantage of your tutorials this week. Get further help and further answers to any questions that you might have in advance of the test next week. Yeah, I'll get it down from up there. Could someone bring the register down, please?